Welcome back everyone to Math TV with Professor V. This video lecture is for introductory statistics. We're going to be going over sections 5.3 on the binomial distribution and 5.4 on the Poisson distribution. Now, many applications of probability and statistics concern the repetition of an experiment, and we call each repetition a trial. We're particularly interested in cases in which the experiment or each trial has only two possible outcomes. So some examples: flipping a coin, because the outcomes are either heads or tails, two outcomes only. Another example would be the driver's license exam. Either you pass or you fail. Or sampling people and determining whether they speak more than one language fluently. The answer would just be yes or no. So these are examples of experiments that have only two possible outcomes. When we repeat trials of an experiment like this, they're called Bernoulli trials, as long as the three conditions listed below are satisfied. So the first condition is that the experiment or each trial has only two possible outcomes, and usually we denote S for success and F for failure. So you could, you have to determine which one's a success, which one's a failure. Don't put like a positive and negative connotation on things. You might decide success is flipping a coin and it landing heads, and then failure would then have to be tails, okay? But it's not like one is better than the other or more preferred necessarily, okay? That's just the terminology we use. The second condition is that the trials have to be independent, meaning that the outcome on one trial in no way affects the outcome on the other trials. So if you think about it, flipping a coin is a perfect example because the result of one coin flip will not impact the result of any coin flips that come afterwards. And lastly, condition number 3 for a Bernoulli trial is that the probability of a success, which we usually denote with p, little lowercase p, it remains the same from trial to trial. So again, back to our coin flipping example, the probability of a coin landing heads, we use 0.5. We're just going to assume it's a fair coin. And every single trial, that probability is consistent. It's always 0.5. It's not changing from one trial to the next. So these are the three conditions that need to be satisfied for an experiment to count as a Bernoulli trial. And the binomial distribution is the probability distribution for the number of successes in a sequence of Bernoulli trials. So if you want to compute the probability that a particular event occurs a certain number of times, then you would use the binomial distribution. So here's the Bernoulli probability formula. Same thing, binomial distribution probability formula. Let capital X denote the total number of successes in n Bernoulli trials. So here's what has to be given. How many times you're carrying out the experiment. So 100 coin flips, 50 coin flips, that needs to be given, okay? And then X is going to be the specific number of successes. So you're going to say, I want, 3 times it lands heads or more than 4 or whatever. That has to also be specified. And you also need to know what the probability of success is. What's the probability that the coin lands heads? Then the probability distribution of the random variable X is given by the following. So the probability that random variable X is equal to some specific little x is equal to, now this, if you haven't seen this before, the way you read it out loud is you say n choose x, and then this is lowercase p raised to the x times 1 minus p raised to the n minus x. Oftentimes we'll refer to 1 minus p as q. So remember, lowercase p, that's the probability of success. And then q, which is 1 minus p, that's the probability of failure. And it makes sense that q should be 1 minus p because remember, for these Bernoulli trials, there's only two outcomes. So the probability of failure is going to be 100% minus success or 1 minus as a decimal. Okay, the random variable capital X is called a binomial random variable and is said to have the binomial distribution with parameters n and p. Okay, so those will have to be given to you. Those are the parameters. Now, the good news is you're not going to have to memorize or use this formula by hand in this class. We're going to be using StatCrunch to compute all our probabilities. So I'll show you how in just a little bit, exactly how to open up StatCrunch and get it to compute the probabilities that you need so you can get through your homework exercises. Okay. Another thing you're going to have to compute is the mean and standard deviation of a binomial random variable. And remember, when I showed you the probability formula up above, we said that the parameters were n and p. Okay, so those have to be given to you. If you need to find the mean, mu, it's equal to n times p. So you just multiply them by each other. And then the standard deviation is the square root of np times 1 minus p. Another way I like to think of it is that the variance, let's go there, sigma squared, is npq, because remember, 1 minus p, that's the same as q. So then if you need the standard deviation, sigma, you just take the square root of that, so it would be the square root of npq. And you can see that's actually exactly what we have here. Square root of n, p, there's q. I just think it's easier to remember it that way, but you do you, whatever you like, okay? So let me just, by hand, let's crunch one out before we get into an example with your homework. So for example, say you're given, you would be given this, that n is 6, p is 0.4, and say you're asked to find the mean and the standard deviation. So the mean, mu, is equal to n times p, so it would be 6 times 0.4, which is 2.4. And then I like to get the variance first. Sigma squared is npq. Well, we have n and p. Can you figure out q? Remember, q is 1 minus p. So 1 minus 0.4, that's 0.6. So npq would be 6 times 0.4 times 0.6. Very good. And this gives us 1.44. I'm not worrying about rounding right now. We're just writing all the decimals, okay? And then to get standard deviation, we just take the square root of the variance. So square root of 1.44 is 1.2. All right. So you'll need to do that as part of the homework exercises. So I just wanted to show you by hand how to compute it. It's not too bad. And now let's just jump into an example from your homework. All right, so let's get into a homework exercise so I can show you how to use StatCrunch for binomial distribution exercises. The probability is 0.3 that a traffic fatality involves an intoxicated or alcohol impaired driver or non-occupant. In 9 traffic fatalities, find the probability that the number y, which involve an intoxicated or alcohol impaired driver or non-occupant, is. Part A says exactly 3, at least 3, and at most 3. So there's no data table to click in this exercise that's going to prompt you to go to StatCrunch. So you're going to need to go down here where it says get more help and then click StatCrunch. That'll always be there for you. All right, now let's see if we can open up the calculator and then identify what the parameters are. So you're going to go to Stat, this time Calculators, and then go over to where you see Binomial. That's the one we want. And we have to identify what n and p are for this distribution. So notice here, p, the probability that of traffic fatality involves an intoxicated or alcohol impaired driver, is 0.3. So that's p. Could you find n? N is 9 right here, okay? 9 traffic fatalities. So I'm going to enter those in here. N is 9. P is 0.3. And then for part A, they want the probability that exactly 3 traffic fatalities involved an intoxicated or alcohol impaired driver. So that would be the probability that X is exactly equal to 3. So change this to an equal sign, that X is 3, and then just hit enter. So there's the probability right there, 0.266827793. They want us to round to 4 decimal places. So that'll be 0.2668. Since there's a 2 afterwards, I'm going to leave it alone. Nice work. Thank you. The probability that at least 3 traffic fatalities involve an intoxicated or alcohol impaired driver. At least 3 means greater than or equal to 3, right? 3 or more. I didn't even have to hit compute. Look at that. We're rounding to 4 decimal places again, so 0.5372, since there's a 6 following the 1. 0.5372. Bam. Love it. The probability that at most 3 traffic fatalities. So at most would be 3 or fewer, so less than or equal to 3. And then this would be, let's see, 0.729. The 6 is going to get rounded up to a 7. So 0.7297. Excellent. Okay. Part B, the probability that between 2 and 4 traffic fatalities inclusive. So now you're going to go over here, click, you see how it says between up top? Fabulous. N and P stay the same, and we want between 2 and 4. So let me change those and hit compute. 0.705, I'm going to round that 1 up to a 2. Well done. Thank you. The mean of Y. Okay, so now remember, to get the mean, mu, we take N and multiply by P. N is 9 and P is 0.3. So 9 times 0.3, that'll give you 2.7. You can just do that in your calculator or wherever. Fantastic. And then let's continue. Choose the correct interpretation of the mean below. So on average of 9 traffic fatalities, this many, 2.7, will involve an intoxicated or alcohol impaired driver or non-occupant. That sounds good to me. Let's keep reading the other options though. On average of this many traffic fatalities, 1 will involve an intoxicated, no. It's not out of 2.7. The mean is 2.7. B is sounding crazy. And then C, in every 9 traffic fatalities, exactly this many will involve an intoxicated or alcohol impaired driver. No, the mean doesn't tell you exactly how many for every sample size of 9. This is just an average. So some may be more, some may be less. So A is still my choice. Final check, yes. And then last, we have to find the standard deviation. So remember, standard deviation is N times P times Q, and then you take the square root of all of that. So Q is 1 minus P. Q is going to be 0.7. And you can just do this in your calculator if you want. I'm not going to write it out. It's a pretty basic computation. So N is 9 times P is 0.3. times Q is 0.7, this gives me the variance, 1.89. They want the standard deviation, so take the square root of that. And we're going to round to 2 decimal places, so 1.37. I want you guys to see. So you'll need to have like a basic or scientific calculator with you too, when you do your homework sometimes or for the midterm and final. Okay, but you'll always have StatCrunch. Don't you fret. All right, the next distribution that we're going to consider is the Poisson distribution. My French is not so great, but I'm going to do my best to pronounce it properly. And this distribution is named in honor of the French mathematician and physicist Siméon Poisson. And literally translated, I mean, it's a last name for a lot of French people, but it means fish too. If you see on a restaurant menu, Poisson du jour, it's fish of the day. So anyways, What is this distribution when we are looking at it statistically speaking? It's used to model the frequency with which a specific event occurs during a particular period of time. Okay, so that's the difference. Time is also a factor. So some examples when it would be appropriate to use the Poisson distribution. If you're interested in looking at the number of patients who arrive at an emergency room in a specific window, like say between 6 and 7 p.m. Or if you are looking at the number of alpha particles emitted per minute by a radioactive substance, or maybe the number of earthquakes during a 1-year period of time. So time is a factor in all of these scenarios. And here's the Poisson probability formula. So probabilities for a random variable x that has a Poisson distribution are given by the following. So the probabilities are equal to e to the negative lambda, this guy right here. Let me highlight it first. That Greek letter, this is lambda. Let me spell it properly. Lambda. Okay? E to the negative lambda times lambda to the x over x factorial, where lambda is a positive real number. Again, lambda will be given to you, okay? And then E is Euler's constant, okay? So E is approximately 2.718. That's a constant. That's not changing. It's an irrational number. You guys probably know about pi, right? 3.1415926, etc., etc. So E is another irrational number that occurs in a lot of mathematical and formulas, as well as physics and other places. And you can study it more in other classes. When you pronounce Euler, though, see, the mathematician, he spells his name like this, but don't say Euler. Otherwise, you'll embarrass yourself at a math conference, maybe, huh? So say it Euler. Pronounce. I'm always looking out for you guys. Okay. Most calculators will have an E key. You don't need to worry because we're going to be using StatCrunch. Unless you don't want to, you can find the key on your statistical calculator. And the random variable x is called a Poisson random variable and is said to have the Poisson distribution with parameter lambda. Okay. Again, don't worry about memorizing this formula. You're not going to even be working with it by hand. We're going to use StatCrunch for our calculations in this class. And the only other thing to remember is finding the mean again and standard deviation for this random variable, but it's pretty easy. The mean and standard deviation are as follows. Lambda, the parameter they're going to give you. So the mean is equal to lambda, bam. And then the standard deviation is equal to the square root of lambda. It's really that straightforward. Okay, so let's jump into StatCrunch now and look at some examples. Okay, Poisson distribution time. The modeling and solution of problems concerning motel reservation networks for motels were studied. Researchers defined a type 1 call to be a call from a motel's computer terminal to the National Reservation Center. For a certain motel, the number X of type 1 calls per hour has a Poisson distribution with parameter lambda equals 2.6. Complete parts A through E below. So first thing we're asked to do is determine the probability that the number of type 1 calls made from this motel during a period of 1 hour will be exactly 3. So we need our StatCrunch. I'm going to fetch it from down here. And this time we want, let me make this a little bit tinier so we can see both windows. Okay. Stat, calculators, and then go down. See how there's Poisson right here? Fabulous. Now it asks you for the mean. And remember, we looked at the mean for a Poisson distribution. It's equal to lambda. So they told me lambda was 2.6. So that's what you're going to put here for the mean. And for part A, they want the probability that exactly 3, so that X is equal to 3 calls were made. So change it to equals 3. And then this time they want 3 decimal places. Okay, not 4. So notice it's 0.2175. So I would round that to 0.218. Excellent. Okay. Determine the probability that the number of type 1 calls made from this motel during a period of 1 hour will be at most 3. So at most 3 means 3 or less. So less than or equal to 3. So this is going to be 0.736. We're only rounding to 3 decimal places. Well done. Thank you. Determine the probability that the number of type 1 calls made from this motel during a period of 1 hour will be at least 5. So at least 5 means 5 or more. So that would be greater than or equal to 5. 0.1225, I'm going to round that to 0.123. Nice work. Find and interpret the mean of the random variable x. So remember, the mean is equal to whatever lambda is. In this case, the mean is 2.6 calls, and therefore the mean tells you on average how many, so just enter it again here. The mean represents the number of calls per hour from, it says, from the computer terminal to the National Reservation Center. So from the motel's computer terminal to the National Reservation Center. Check. Excellent. So that's it. I do want you to know, if you, I didn't finish. Find the standard deviation of the random variable x. Remember, standard deviation is just the square root of lambda. Lambda was 2.6. So just type that in, 2.6, and then we're going to take the square root, 1.612, if I'm rounding to 3 decimal places. Let me scoot this down. 1.612. Excellent. Okay, I do want you to know, a lot of times view an example is super helpful, but the homework doesn't know necessarily that I'm allowing you to use StatCrunch. Not every instructor does. Some will make their students do everything by hand with the formulas. So when you click view an example for these exercises, they will show you how to plug everything in by hand, which is not necessary for this class. If you're really compelled to want to practice it that way, go for it. But on a lot of these problems, I'm showing you how to do it with StatCrunch because view an example will not align with what I'm okay with you doing. Okay, good. So that's the end of that example. I think you guys will have an easy enough time with your homework.